Well, good afternoon, everyone. Well, for those of you in the eastern side of Australia, I guess, welcome to another Toolbox Tech Talk with me, Glenn Morris from the Smart Energy Lab. And today's all about the string theory. Yeah, not theoretical physics, just good old PV string theory. So it does sound like an episode of the Big Bang Theory. Thanks. There's Bradley just giving me a plug. Thank you, Bradley. I think you get the award for my most regular attendee. In fact, you're the first person to come in via LinkedIn, so I wasn't even sure whether that worked. So, that's great. I'm getting comments from LinkedIn now. Thanks very much. So it's all about string theory today and understanding, I'll press the wrong button, understanding how to consider when you need to have string overcurrent protection. And I often talk about things on Toolbox Tech Talk that came up during the week, and this is one of them. I had some questions from previous students about string overcurrent protection, and they raised some interesting side issues as well, which we'll talk about: array cable sizing and short circuit rating of PCE or inverters or charge controllers. So I'll get my eyes back into gear. That's great. And just for those of you who are new to the show here, I'm not a bad boy hip-hop artist. It's just a bit of a fun thing to do on a Sunday afternoon. It's all about solar and battery storage systems and electrical theory relating to solar and batteries. So that's what we'll be talking about. Thanks for the background music plug. It is royalty-free, so I can stream it, so that's great. I should even credit the author sometime. I'll have to check to see who that was. So today's about string theory, and I wanted to point out also a bit of a plug for my training courses that I run on a regular basis. I've got a 5-day course starting tomorrow, actually, for those who are interested in solar and battery design. It's 4 hours a day, starting at 8:30 Melbourne time, so 4 hours a day, Monday through to Friday, and it's all delivered online via Zoom. So it's a classroom environment where people join and we can all see each other and talk to each other. And as you'll see in a minute, I use overhead projection of drawing devices, so I can virtually have a classroom. So it works really well for me as a training environment, and I make it as interactive as possible. All the sessions are recorded and shared with the participants afterwards. So a lot of people can't commit to 5 days in a row, so they just do catch-ups. They catch up on the bits they missed out. And there's also, so it's practical. So there's practical in terms of you get some assignments to do, you bring those back to the class and we work on them. So the intent is to give people the skills and knowledge to design standalone and hybrid battery and solar systems to Australian and New Zealand standards. So that's kind of the principle of the course. It's actually open to anyone who wants to do it. You don't have to be an electrician or electrical engineer, though a basic understanding of electrical theory would be very helpful, but it's not essential. So a lot of it is just explaining common sense around understanding load energy and how to size for it. So anyway, there's a plug for my course coming up this week, starting tomorrow, actually. Also, I'll be doing some specialist courses just on the battery standard, AS/NZS 5139, and also some for electrical inspection, or mostly it's aimed at electrical inspectors, but actually most of the courses are half electricians, half electrical inspectors. I guess the electricians want to make sure they know what they're doing before they get inspected. And those courses are all on my website, so solarquip.com. You go to solarquip.com and you can see the courses there. Anyway, enough chit-chat, and it's great to see people throwing some comments in there. Thank you Mansingh and Rumi and Bradley. So you can press the like button, or if you're on Facebook or YouTube, it's always great just to kind of push up the channel a little bit there. And also feel free at any time to ask questions or make comments, because I can see them as they come in and I can bring them on screen and we can discuss stuff. So the idea with these Toolbox Tech Talk is I've got a theme, but they're interactive. So please feel free to critique or ask questions about what I'm presenting. So let's go to the problem. The problem it starts with, and this is where I'm going to bring up my drawing. So I'll just bring this overhead drawing here. The problem starts with understanding the ratings for cables in a PV system. And Sam just asks, thanks, Sam. That's great. I'll just bring this one up. Sam says, will you be covering worldwide specifications and regulations? Sam, it's kind of a big ask to cover the whole world. But a little bit of background. Most of this is to do with AS/NZS 5033, which is the PVRA standard in Australia and New Zealand. It actually was the first national standard for PVRAs and was largely wholly adopted by the IEC, the International Electrotech Commission, to produce a similar standard. We've got representatives on that committee. So you could say, in a way, 5033 is mirrored at the IEC level. I can't remember actually the IEC number, but so in a way it is covering global considerations. A lot of this is just basic electrical theory too, so applying it to a PV system. It's not like some special rule just to make life hard for you. So yeah, thanks for that one, Sam. Let's take Sam off. There we go. And I got my first thumbs up. Thanks, Robert. Really appreciate a thumbs up from now and again. It's amazing. Everyone's coming from LinkedIn. I really had no comments from LinkedIn up until today. And what do you know? It's all LinkedIn. LinkedIn is winning on the comments field. So those people in YouTube land and Facebook and Periscope, etc., go for it. All right, so let's look at the problem. Now, defining my terms is pretty important to start with. So let's talk about how we describe cables within a PV system. The first one is the string cable. Now, a string cable in a single string system is pretty hard to differentiate from the array cable because there is only one cable. But it's the cable that connects the panels together, and the array cable is the cable that comes from wherever the array happens to be to wherever the power conditioning equipment is. Now, I've used the acronyms that are in the standard. So PCE, power conditioning equipment, see I've just put it down there as a little asterisk, power conversion equipment, or conditioning equipment actually it is, I just realised, is anything that modifies voltage, current or frequency. So PCE, anything that modifies voltage, frequency or current is PCE, and that would cover things like inverters, obviously, and also charge controllers, but even things like direct powered appliances are PCE. So something that might heat water using variable current, something that might operate a pump that turns a motor, for instance, that's PCE as well. So really whatever's here is irrelevant. It's same principles apply. So I've try to make this a practical example, and I've got 3 drawings which I'll extend through as we go. Thanks, Facebook user. Always here on Sunday from Facebook. Great, from Geraldton. Wow, I guess that's Geraldton, WA. Missing WA. Used to go over there quite a lot, but it's been hard to get anywhere lately for obvious reasons. So let's look at a practical example. I've used a data sheet from some panels which, interestingly enough, we were installing today. These are the Longy solar panels, these ones here. We're installing a combination, actually, some of the mono-perks and some of their bifacials, but this is the mono-perk. And it's pretty typical of the new large size panels. We're seeing, panels, particularly utility scale panels like these, which are 2 meters long by 1 meter wide, so they're really big panels. Not really ideally suited to residential homes because of the purlin space or batten spacings on a roof, but for utility scale, big is good. Less stuff to stick onto a mounting system. And we look at the data sheet for this one, and I'm going to zoom in on it for you because we need to know some specs. Now, most data sheets cover all of the modules, so I'll zoom right in there. Here we go. That's it. I think I've gone a bit too far. I'll come back a little bit. And a bit more. There we go. So this is the data sheet for a range of solar panels. If you're not familiar with solar panel data sheets, they often grade the cells and put them into multiple packages. So we've got the 420 watt, so the 425, the 430, the 435, and the 440, all are physically the same panel, like in terms of dimensions, weight, electrical connections, etc. The only difference really is the conversion efficiency of the individual cells they put into those panels and therefore their output power. Mostly it's about current and to some extent voltage, but what you'll see is that the operating current of these panels, so where are we? Maximum power operating current, so the current at maximum power here, and they give two values. They give NOCT, so that's normal operating cell temperature, which is kind of a conditions that are more typical in real-world applications, such as not full irradiance. I often call this the European test because in Australia, 800 watts per square metre is not even trying. We've got very clear skies here in the southern hemisphere, lack of pollution, I guess, and so 800 watts per square metre is not even trying. 1,000 watts per square metre is pretty much the middle of your day, even higher when you've got the right conditions. But anyway, it's a more typical performance, but most of the electrical calculations for solar panels are based on standard test conditions. So we'll just ignore NOCT and we'll look at standard test conditions. And so the panel I'm looking at is the 435 watt Longi solar panel here, and its operating current is, where is it down here, 10.67 amps. But we're not really interested in its operating current. We want to know under fault conditions how much current can flow. Now, the thing about solar panels is they are a current limited source. Unlike a utility grid, which is kind of almost an infinite source of current, only the fault loop impedance determines the limits, a solar panel has a maximum amount of current, and it's not much more than its operating current. I mean, look at that. The operating current for that panel is 10.67 amps, whereas the short circuit current is really only not even an amp more. So about 6 or 7% more is the fault current for a solar panel when it's short circuited. So we need to ensure that all of our electrical installation, our cables and protection equipment, and right down to the PCE can withstand that fault current. Now, our standard says that anything to do with overload conditions, we need an overload factor of 25%. So we allow another 25% on top of that number just to be sure. And it's for good reason. Because standard test conditions is only 1,000 watts per square metre, and in the right conditions, you'll get higher than 1,000 watts. And the current output of a PV module is pretty well proportional to irradiance. So you increase the irradiance, you increase the current. So it's not unusual to see 10% more irradiance under the right conditions. I've measured over 1,100 watts per square metre here on my pyranometer at the Smart Energy Lab. And so those sort of conditions mean you get another 10% of current. So hence our overload factor of 1.25 times. So I've used this module for the purpose of this exercise. And I'll just zoom back out so you can see. There we go. I'll come in a bit. So there's the module. There's its short circuit current at standard test conditions. I should have put an A there, so it's A for amps. And we need to ensure that the cable can carry 1.25 times that. So really 1.25 times 11.2 is 14.1 amps. So it's not very big. Shane, that is why we've got that overload factor. It's just to ensure that you never thermally overload the panels under any conditions, or the cables, sorry. So there's your 14.1. Now, most PV arrays, certainly a single string on a residential installation, are probably going to use 4mm cable. So we might have 4mm square so PV cable here, and PV cable is a tougher cable. It has a higher temperature rating, typically better than your standard 75 degree cable. That's definitely more like 90 degree cable. So we need to check that cable can withstand that current. So this is where you dive into the wonderful cable current standard AS3008, ASNZS 3008, and I've just zoomed in on a little section of it here, which is specifically for cables that are multi-stranded. And this is just got to get it so you can see it all nicely. A 2-core cable enclosed in air, so basically in conduit. And so you've got a cable and conduit against a surface, and it's rated to 90 degree cable, so it's maximum operating temperature. And for 4mm flexible conductors, we can get 37 amps. So 4mm cable is good for 37 amps in conduit against a surface with a 90 degree rating. So will our 4mm cable do it? No worries at all. Our 4mm cable will be absolutely fine, carrying 14.1 amps. So if this was 90 degree C cable, and therefore approximately 37 amps current carrying capacity. So all good so far. So we're not damaging our cable. Now you might wonder why, and I've been asked this from people who are new to solar, why there is no overcurrent protection required in a PV array connected to, in this case, a grid tie or grid connect inverter. What about, a fault condition? Wouldn't you just put a circuit breaker or fuse in the string cable to protect from overcurrent? The problem is it doesn't work. Because you've got a current limited source, remember these panels only put out about 7 or 8% more current when they're short circuited than when they're operating. You just don't have enough differentiation between normal current, so operating current, and short circuit. So that discrimination is too fine for overcurrent protection devices. But in a way, you don't need it anyway because your cable sizing is your overcurrent protection. So the fact that your cable can carry 37 amps and you're only pumping through a maximum of 14.1, your cable is your current overcurrent protection. But now comes the rub. There's another step in this process, which is in a fault condition where you may well have a fault on the PCE side. So let's say this inverter chooses to short circuit the array. And so we've got a fault here. So there's a fault internally. We still have to ensure that not only the cable and PV modules are thermally protected, and presumably the panels are thermally protected because they're rated for their own current. That makes common sense. And that your cable sizing can carry that current, therefore it's protected. But the inverter itself needs to be able to carry that fault current of, in this case, 14.1 amps. So how do we find out what the internal short circuit current rating of an inverter is? Now, this is why this question came up this week from one of my former students, and he sent me this data sheet for an inverter, and he said, "Oh, Glenn, it doesn't look like it's going to work." In fact, he was using a very similar panel to these longies, and so here's the data sheet for the inverter. So I'll just bring that over here so you can see it. There we go. And he was looking at this figure here, the maximum input current rating. So the maximum input current DC1, DC2, that refers to the two MPPTs that are part of this inverter. And it says 12 amps. But that's not a short circuit current rating. So he was worried that his panels could put out, allowing for the 25% oversizing factor, over 13 amps. And he was going, well, this inverter can't cope with that. But that is a current limiting factor. It's not a short circuit current rating. Now, this is where it gets tricky because it sounds like it's a maximum, but it's a maximum of current that the inverter can convert. It's not a maximum of current that the inverter can pass through under fault conditions. So you actually need the short circuit current rating of the inverter to find out will these panels be suitable for this particular PCE. And it's nowhere to be found on the stock data sheet. So we looked at the stock data sheet and it doesn't mention short circuit rating. So we actually had to go to the product itself, and on the side of the product was this. So a sticker on the side which said ISC 13.9 amps. Right, so it took a bit of research really to find out whether this inverter was suitable for this particular panel type. So remember that number, 13.9 amps is the maximum ISC. So actually I can't use that inverter with this system because I'm up at 14.1. So 13.9 amps is just a squidgen too less, and it's all about exacts. So just a little bit too less is too less from a compliance point of view. So that would mean I would choose a different PCE for these panels or change the panels with a lower current rating. So that's step one. We're finding out, can we match our PCE short circuit current rating with the short circuit current rating of the PV array? Step two is, let's say we're going to put in more than one string. And this is where the special clause in 5033, our PV array standard, comes in, which is at which point do we need to protect strings from each other within an array. So, next drawing. So you with me yet? I'm looking for any questions for clarification. I don't want to rush too fast, so feel free to throw some questions in there or comments even. So here we've got two strings. Now let's imagine we're using a PCE here which does have an ISC high enough to cope with, and there's the formula. The cable must be rated for 2 times the short circuit current plus the so the overload factor of 1.25, which means the cable must be good for 28.2 amps. And we already saw that, for instance, if we're using 4mm square solar cable, it would be good for enclosed and conduit against the surface for 37 amps. So no problem there. 37 amps. That's fine. Okay, so that solar cable's plenty big enough, and we've chosen an inverter that can cope with an ISC of 37 amps on its input. So that's all good. But the question is, and this is where I'm going to have to draw some faults in this situation, is if we have a fault in one string. So I've got a fault to earth here. Now, because virtually all PV arrays, certainly in Australia and New Zealand, are floating with respect to earth, that means there's no earth reference, no functional earth. In fact, that's pretty normal everywhere because of transformerless inverters. You can't galvanically bond a transformerless inverter on the DC side. You basically blow it up. So we need 2 faults for anything bad to happen. So I'll add a second fault. So I've got a second earth fault here. There's my second fault. And so now I'm going to get some circulating current within the array because I've provided a loop path. And what's going to happen is the current, conventional current flow. So this is my fault current. My conventional fault current, or conventional flow of current, will go up here and down this way, then all the way around to the second fault, and then pass back through. So that becomes the circulating current. Now there will actually be a very small secondary flow because of Kirchhoff's current law, if you're familiar with that. There will be a very small flow going to the PCE, mainly because of impedance, depending on what the impedance of this part of the circuit is. But effectively, our panels in string, well, I should give them names. So this is A and this is B. And string B is supplying its fault current, which is 11.26 amps, into string A. And therefore string A has to carry in reverse 11.26 amps. Now, the first thing to consider is there a thermal overload possibility with this arrangement? Could we actually exceed the current rating of the panel? Now, we looked up the data sheet before of the panel. I'll just bring it back up here for you. And up the top of that data sheet, if I zoom right in on it, is what they call the series fuse rating. And maximum series fuse, there it is, 20 amps. So the maximum series fuse is 20 amps. Now technically it's known as the maximum reverse overcurrent protection rating, which is such a mouthful no one ever puts it on a data sheet. The test for modules is that you reverse the test current, so the manufacturer declares what their rating is. The test lab will reverse that current through the panel, which makes it heat up, because operating a panel as a load just makes it heat up instead of producing electricity. And they lie it on a sheet of tissue paper, and then they put some muslin on the back of it, on the back sheet of the panels, and run that test current for 2 hours through the module. So they're running 20 amps through this module for 2 hours. It sounds very archaic, this muslin and tissue paper, but the purpose is to see if there's any scorching. So after 2 hours, they stop the test and inspect the tissue paper and the muslin. There should be no scorching on either. So you haven't thermally overloaded the module. So that means this panel can, under fault conditions, accept up to 20 amps. And they call it a series fuse rating is because the most common way of limiting that current is to use a fuse in the string. And the maximum size they recommend here is 20 amps. So remember that this module can take series fuse 20 amps. So series fuse 20 amps. Is 20 amps greater than the fault current? And the fault current here is 11.26 amps. So the question is that greater than that? No, it's not. We're pushing only half that through the panels. So there, in this situation, there is actually no requirement to thermally protect the faulty string. So a way of saying this really is the number of strings in parallel minus 1, because the faulty one doesn't contribute to its own demise. So the faulty string doesn't basically work. It's just a load. So the number of strings minus 1, the fault current of that, so in this case there's 2 strings, minus 1 is 1 string, times the short circuit current of a module must be less than the series fuse rating. If it's more than, that's when we have to introduce some protection. So at this point, this diagram's all good. So our cable's big enough, our panels can carry the reverse current when one string is faulty. The power conditioning equipment can carry at least the 28.2 amps short circuit current on its MPPT input. So no additional equipment required. We just made sure we selected the right inverter to suit this array. You're all very quiet at the moment, not getting any questions, because we're coming up to the last slide now where it gets a little more complicated. So here we've got 3 strings. Still the same panels. We're still talking about these panels which have 11.26 amps. So the ISC of each one equals 11.26 amps. And we've got 3 strings. And therefore, the maximum current we can get could be 3 times this. So let's just work this one out. $11.26 times 3 strings, and then we've got to put the 25% safety margin in there, so times 1.25, which brings us up to the cable must be rated for greater than or equal to 42.3, let's call it 2 amps. There we go. So as long as the cable can carry 42.2 amps, and incidentally that means we're not doing 4mm cable anymore, it's just not big enough. It only goes up to 37 amps. So at this point we'd actually have to change our cable, so therefore we'd have to go to 6mm square cable with those 3 strings, and we could double check from our table here, and it tells us 6mm is good for 46 amps. So 46 amps, just squeeze in there. We just squeeze in. So so at 90 degrees, it's good for 46 amps. Okay, so that's all good. Tick, tick. We make sure that our PCE can carry at least the fault current of up to 42.2 amps on its input. So the input short circuit rating of the inverter is 42.2 amps. But now we have a third and bigger problem. The bigger problem is that if we were to have that same earth fault here, and of course the secondary fault elsewhere, we've now got 2 good strings back feeding. So that one, 11.26 amps. This one, 11.26 amps. They sum together at the point that they combine. And the reason, by the way, these are fuses, you'll see why in a second, that I've shown them there, is that we could now get the sum of the 2, which is 22.5 to 52, so 22.5 amps flowing this way. Okay, so sorry, Nick's asking what table number do you use for 388 for PV array cables? Well, it does depend on what temperature rating, because some PV array cables are 90 degrees, some are 120 degrees. I know the Radox cable we have here at the lab's 120 degrees, so that will determine what table. But I was using table 5 just then, which was for 90 degree 2-core, and I was using column 16, which is for enclosed in air against a surface. Yeah, so basically in conduit, and using flexible conductors. So that's where it came from. So thanks for that question, Nick. For those not familiar with 3008, it is quite a learning process to get your head around, because there's so many tables and so many different configuration options. Knowing which one applies can be a little bit daunting at first, but once you've got it nailed, put a little post-it note on your copy, and you'll go straight to it, because generally you won't be using a wide range of cables. So thanks for that one, Nick. It's good to have clarification on this. So coming back to this one here, we've now got 22.5 amps under a fault condition. Now we don't have to put the safety margin of 1.25 on that. That's only for the PV array cable. As far as our series fuse requirements, is whenever we exceed the series fuse rating of a module, which in this case the series fuse was 20 amps for this module. So this module is rated for 20 amps. We've exceeded that under a fault condition. We've effectively triggered the requirement for string overcurrent protection. Now, it's very important, because I hear this misconception a lot. It's not about the number of strings. It's got nothing to do with the number of strings. It's the ratio of that to that. That's what makes all the difference. So, I mean, you can get modules with up to 35 amp series fuse rating these days. So if that was 35, we wouldn't need those fuses, because 22 amps is less than 35. See what I mean? So it's all about the ratio of those two. But it's very common at 3 strings in parallel to get to the point where it is likely that you're going to have this happen. So my kind of shortcut for making a decision here is 1 string never needs string overcurrent protection. 2 strings never need string overcurrent protection, because as long as they're the same modules, they're not like some little tiny modules in parallel, the big powerful ones. But when you get to 3 strings, you need to consider it. So don't just automatically do it. So Mike's just asked me, so Mike says, let's have a look here. PV cable, 4mm, 30 amps, 6mm, 40 amps, question mark. Well, it depends. You can use 388 or the manufacturer's recommendations. So it's up to you how you limit your or rate your cable. But 388 is the guidance for Australia and New Zealand on current carrying capacity of cables. And it's very detailed, because it's not a simple answer like 4 mils good for 30 amps. It depends whether it's direct buried in ground, and closed in conduit in ground, whether it's open and free air, under insulation. All these factors derate or change the rating of a cable. So it's much more complicated than just 4 mils good for 30. But Mike, that's not a bad number if it is PV cable. So coming back to the string overcurrent protection requirements, we triggered it because our series fuse rating of 20 amps was less than N-1, the short circuit current, N being the number of strings in parallel minus 1, which means there's 3 strings in parallel. We subtract 1 because the faulty one doesn't contribute to its own demise. That means we've got 2 strings in parallel. 2 times 11.26 amps is 22.5, and that's greater than what the module can withstand. So the thermal overload condition of maximum of 20 amps on the module has been exceeded, and so therefore we need to put in string overcurrent protection. Now, I've shown fuses, but it doesn't say fuses in the standard. It says string overcurrent protection. And it says that should be located as close as practicable to the point of combining. So I've kind of drawn it like this, like they all come to one point. So it's probably an isolator or a combiner box, and that's where those fuses would be. Those overcurrent protection devices would be. Now, it is possible to use a circuit breaker as an overcurrent protection device, but unfortunately the overload characteristic of solar is not suited for the standard C curve, D curve, etc. of a circuit breaker. There's just not enough difference between I nominal and I trip for it to operate. So that's why fuses of the type GPV. Now, there's actually a range of fuse types. So solar fuses, well, I'm calling them solar fuses, type GPV. So they have a relatively low trip point compared to their operating current. And so they're designed for the characteristic of solar, which is it peaks for a few hours in the middle of the day. It's not a sudden peak, and it's not a very sustained peak. It doesn't last for like 8 hours. So that's commonly what's done. How do you actually do this in practice? This is where I'll come back to me for a second. What's a popular option is to use cartridge fuses like these. So this is an HRC fuse switch. Now, anyone who's got good eyes and reviews this afterwards, you'll note that I haven't actually used the right type of fuse in my hand because I couldn't find any in the lab. This is actually a GR fuse, which is for general purpose. Generally, it comes out of my Fluke meter, but it's the same physical size. It's your basically 30 mil by 10 mil fuse size, and this is a fuse holder for such. And these are great because there's no live parts when you pop it in there, so you can't touch any live parts. And if I put it in properly, oops, why is that not going in? There you go. And it knife locks in nicely, and so that is your fuse holder. And I think it's even got a little window to tell if it's tripped or not. Now, this is an inexpensive way of adding fuses, but it does mean you've got to put it inside an enclosure, and that enclosure probably might need an IP rating because if it's outdoors. So the costs really start to go up when you put in string fusing. There is other options though, which is you could choose a inline fuse which is in a similar kind of holder to your standard solar connectors. They look like a slightly elongated solar connector, the MC4 type solar connector, but it's got a fuse holder inside it. So that's another way of doing it, is inline fuses within the string. And they're generally IP68. So that's another way of doing it. Okay, so yes, good point, Romney. AS388 is technically for AC cables. You're dead right that the DC resistance is a little bit less. I don't know if 10%, it might be a little bit on the high side, but is less for PVRA or for DC cables. And the reason for that is that DC doesn't suffer from any of the effects such as proximity effect of AC and skin effect of AC. So there's a couple of losses in an AC system which you don't get in a DC system. You only get resistive losses and thermal loading due to bundling. Those are the only kind of considerations. So yes, you're right, it's a little bit less. So 388, not a bad place to go. If you meet that, you'll definitely exceed on a DC circuit. So thanks for that clarification, Romy. That's bang on. Yeah, so the other thing is, what if we look at this diagram, so I'll go back to it now. Go back to this diagram. If we trigger this requirement for string overcurrent protection, what size fuse do we put here? Now, you don't have to put this fuse. You don't have to put a 20 amp. The formula in 5033 is, it's been updated actually. So it's bad teaching practice to tell you the wrong answer, then the right answer, but I'm going to do that right now. Way back in the 2005 version, I think it was, we said that the minimum fuse size is 1.35 times the ISC of the module. And the problem with that was we were seeing false tripping occurring. You might think having a 35% safety margin between your operating current, your short circuit current of the module and your fuse trip point was plenty, but it wasn't. And the reason why it wasn't is all the ducts can line up. Now, if you haven't heard this saying, a whole bunch of things can happen at the same time. You might actually have the fuses in a high temperature location, like on a roof, so they're sitting up at 60 degrees ambient, so they'll derate a little bit for temperature, so you might lose 5% due to temperature. So their trip point might have been 15 amps, but it's dropped to 13.5 amps now because the fuses are at 60 degrees Celsius. Manufacturer's tolerance, they might be plus or minus 3% or 5%, so that you might actually have some of the low tolerance fuses. And the third one is, you can't assume that ISC at standard test conditions is at the actual highest current because of high irradiance conditions, sometimes called the cloud edge effect. So this can happen when you've had particularly a storm and the sky is very clears, the storm clouds clear, and behind those the clear sky is some very tall cumulus clouds that reflect a lot of white light off the sun. So you get direct beam sunlight, a high amount of indirect reflectance of white, very clean white clouds, and that can give you another 10 or 15% irradiance. So if you get 15% more irradiance, 5% manufacturing tolerance, another 5%, you're starting to get so close to that 35% overload factor that we were seeing false tripping. And so we pushed it up to 45% higher than the short circuit current rating as the minimum series fuse rating. So another question's come in. Let's have a look here. So Ray's asking, would the MIDI fuse that reduces, that Red Arc use, I can't even read. Would the MIDI fuse that Red Arc use for BCDC, I'm not sure what BCDC is, be okay fuse for a string? Ray, I'll try and interpret what I think you're saying. When you say MIDI fuse, inline fuse, if it's an inline fuse that's appropriately voltage rated, so it's suitable for applications for PV arrays, which generally, there'll be a 1,000 volt rating or even a 1,500 volt rating for plugs and sockets. So therefore, your inline fuse holder should be similar. And if the fuse type is GPV, suitable for PV applications, then yes, Ray, I think that will be fine. MIDI inline. Okay. I'm not quite familiar with the product, Ray, so I'll just leave it at that. So it sounds like it's probably okay, but you should always check the ratings that they're suitable for both the voltage and the trip characteristic of solar. So, going back to that explanation, I'll bring up the drawing one more time. What rating do we put for that fuse? It's got to be 1.45 times ISC, but less than the series fuse rating, less than or equal to. So that means 1.45 times 11.26, but less than 20. So that's the range. And it does give you one more condition, which is and less than, so it's got an and less than 2.4 times ISC. And in most practical circumstances, you never get to 2.4 times ISC because the series fuse rating is less. But there you go. It's that those are the three conditions that you need to meet. Oh, questions. Thanks, Ray. And I see Jack's just clarifying here for my benefit that MIDI are an automotive fuse, not GPV. Maximum 32 or 60 volts. Well, some PV systems are extra low voltage, what's probably now better thought of as DVCA. So you might get away with it in an off-grid system operating at less than 60 volts, but certainly not in a conventional PV array that's operating at hundreds of volts. Yeah, so thanks for that one, Jack. Really important. So just coming back to that range, my recommendation, by the way, is always use the maximum. Always try and go to that fuse rating that the manufacturer specifies. The reason for that is you just don't want false tripping in a multi-string system, and this is because you just don't know it's happened. If you've got 3 strings and you lose one, the customer probably will never know. In fact, embarrassingly, this has happened to me. I had a customer, and this was in the days when we were allowed to use 1.35 times ISC. I had a customer come to me and say, look, Glenn, the system's not working so well that you installed like 7 or 8 years ago. I think I need more panels. And, many people just assume they're using more power. So, we got up on the roof ready to sort of put in more panels, and I checked the fuses and one string had blown. And what do you know? It was just too close. The rating was too close. And so it had probably blown years ago. And so her 3-string system had been a 2-string system for some years. So that's why we increased that minimum rating for a series fuse to 1.45 times. So Nick, questions. Nick, do you need, here we go. Nick asks, do you need 2 faults to earth on a PV wiring for fault to flow? Yes, you do actually. So the situation in a floating array, as I've drawn it here, is that a single fault, if I had only this fault here, I've earth referenced part of the DC system, but without the second fault, there is no current path because the inverter is transformerless, doesn't provide a galvanic connection to earth when it's not operating, certainly, but that fault condition in terms of the current flowing within the array requires a hard earth second fault in the array itself. Sorry, that's a little bit clumsy answer for you, Nick. Couple more questions. Yes. Do I remember these? I've got a lot of the Canica 60-watt panels here. In fact, I've got a lot of the 120-watt panels too, mainly because customers wanted more solar and they were just too small. Like 60-watt panels took up a square metre. They were pretty low conversion efficiency, and they had a very low string fuse rating of only 3 amps. And because they were a high voltage panel, they put out 100 volts each, most systems had lots of strings, typically 4, 5, maybe even 6 strings on a residential system. So you often triggered that string fusing at around the 4 or 5 mark. And Facebook user says we have masses still going. Yeah, nothing wrong with them. In fact, I've actually repurposed a lot of them for shade devices on the side of my house and on the side of my shed, and they're connected to inverters. They're just that they take up a lot of space for a relatively small system. But yeah, nothing wrong with them. Amorphous silicon was very popular in the day. It's sort of faded from popularity because of the poor conversion efficiency of only about 7 to 10%. So you've been great today, lots of questions, and I think I've covered just about everything. So this is your last chance to ask some final closing questions around string overcurrent protection. So is it something that you are familiar with, that you've still got some confusion? Facebook user, who sounds awfully anonymous, says, yep, suits C container shading. Yeah, true. I wish I had a picture handy that I could show you of a shade awning I put on the side of my house using Canica panels. They actually look nice too, because, I mean, solar panels, they look nice too, but the conventional ones with individual cells are quite busy, whereas a Canica panel is just a brown square. They're quite, from architectural point of view, they look they blend in well. So, they make great shade devices. So I think I'd wind it up for today. Thanks everyone for attending and coming along to my Sunday Toolbox Tech Talk. Just one more plug for my courses. I'm running a 5-day, 4-hour-a-day course starting on Monday in solar and battery design. It's all online. It's delivered via Zoom. You can register for that course anytime up until 8:30 tomorrow. I even get people registering after the course has started because I actually record every session and you can watch it afterwards if you can't make it. So go to solarquip.com if you want to register for that course. And I've also got courses coming up for just on the battery standard, ASNZS 5139, and also for electrical inspection. So I'm doing electrical inspection courses. I've been doing quite a few of those. They've been really quite popular. And so those are focusing on 3 standards, 5033, 4777 and 5139, purely from an inspection point of view and compliance. We're not doing design in that course. So those are some of the courses that I've got coming up. Otherwise, hope to see you back next Sunday for another Toolbox Tech Talk, and I think I've got a guest coming next week, so that'll be fun. So I'm going back to a guest next Sunday. So thanks everyone. I'll see you then.